Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are indeed shining bright because we are continuing our study of sequences and series, and as you can see, we're going to talk geometric sequences. So we will revisit the great Echo Smith when we finish. Let's get to it, shall we? I think we're going to have two parts. That's why it says part one. Okay, a sequence is geometric if each term can be obtained from the previous one by multiplying by the same non-zero constant. So they have some examples here. I think you can clearly see that we're generating the next term in the sequence by multiplying by 5. The important part is not to think of it as multiplying it by 5 necessarily, but to think of it as a common ratio. Similar to what we did with arithmetic sequences, we compare a term to the previous term. But instead of subtracting, we're dividing, hence the common ratio. So you can see that 10 divided by 2 is equivalent to 50 divided by 10, which is equivalent to 250 divided by 50, which is all of those are equal to 5. So for this particular geometric sequence, the common ratio is 5. And that is what makes a geometric sequence a geometric sequence. Consecutive terms have the same common ratio. And as we talked about in class, this notation here indicates a term divided by the previous term, u sub n plus 1 divided by u sub n. So here we have a common ratio of 5, and here we have a common ratio of -5. All right, so we got that going for us, and this is a little blurb about where the name geometric came from. It has to do with the geometric mean. And then they are telling us what the general term formula is. In other words, to find a particular or specific term in a geometric sequence, this is the formula that we are going to use. U sub n equals u sub 1 times r to the n minus 1. And that formula can also be found in your formula booklet in the same spot as the arithmetic sequence formulas were found. So let me just slap that in there for us because we will be using it for sure. Make it a little smaller, but you can see it is right here. The nth term of a geometric sequence that got a little fuzzy is u sub n. Wow, that should be an equal sign. There we go. U sub n equals u sub 1 times r to the n minus 1. All right, so let's get to it. Consider the sequence 8, 4, 2, 1, 1/2. Show that the sequence is geometric. Let me go ahead and pop that formula on here again. There we go. And things are fairly simple. We do this in the same manner that we showed that a sequence was arithmetic. We compare term to previous term. Of course, with arithmetic, we were subtracting, and here we just have to show that if we compare the term to the previous term, we are always going to get the same thing, which is the common ratio. All of these are equal to 1/2, so that is equal to the common ratio r. So now we have to find the general term, u sub n. Well, this is the nth term of a geometric sequence, so we start with that. U sub n equals u sub 1 times r to the n, oops, that's an m, r to the n minus 1. So all we need to do this are the first term and the common ratio. So for this particular geometric sequence, the general term is u sub n equals u sub 1, which is 8, times r, which is 1/2 to the n minus 1 power. And we had discovered this in class when we had done a couple of the opening number sequences where we saw we could just continue multiplying by that common ratio. And so now we're going to use it to find the 12th term, and we're going to write it as a fraction. So u sub 12 is equal to 8 times 1/2 to the 12 minus 1. And of course, 12 minus 1 is 11. Okay, so that in turn would be equal to, let's see, are we going to write that as 2 to the 11th or, yeah, okay, that's fine. So that's 8 times 1 over 2 to the 11th, which is equal to 8 over 2 to the 11th. And 2 to the 11th is indeed equal to 256. 2 times 2 times 2 times 2 times 2, blah, 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 blah. All right, so we'll do example 8 here. These are consecutive terms of a geometric sequence, so find the value of k. So again, let's think about a geometric sequence. We'll just do a sample one where we multiply by 3, so the common ratio is 3. So we'd start with 2, and then 6, and then 18, and then 54, boom, boom, boom. Well, if it is a geometric sequence, then 6 over 2, term divided by previous term, has to be equal to 18 over 6, which has to be equal to 54 over 18, and they are all equal to 3. Okay, so it's no different than if I had a geometric sequence, k minus 1, then the next term is 2k, then the next term is 21 minus k, and then it keeps going. I mean, these could be anywhere, right? They could be part of this sequence, we just don't know. But we have to find k. So what we're going to do is write common ratios. So we're going to take a term compared to the previous term, 2k over k minus 1, and that's going to be equal to 21 minus k compared to its previous term, 2k. So we cross multiply and we get 4k squared is equal to k minus 1 times 21 minus k. And so 4k squared would equal 21k minus k squared. Expanding this, minus 21 plus k. Clean that up a bit. We get 4k squared is equal to what? Negative k squared plus 22k minus 21. Move everything over to the left side, and what are we going to get? 5k squared minus 22k plus 21 is equal to 0. And this will factor. You can use quadratic. You can split the middle term. I'm not going to go through that here because we should know how to do that. We get 5k minus 7 times k minus 3 is equal to 0. ZPP, yeah, you know me. And we get k equals 7/5, or k equals 3. Okay, and you can check it, like if we put those values substituted back in for k, you could make sure they have the same common ratio, but both of them would form two different geometric sequences that satisfy this requirement. Okay, so for part 1 of this video, we're just going to finish. We're not going to finish. That's going to be it. And so with that, that's the end of part 1. Hope you enjoyed it as much as I did. I thought it was pretty great. So we are going to see how EchoSmith is doing. And I am out. My face. Nights are good, and that's the way it should